This is section 6.3c, vectors. This is our third and final section on vectors. Of course, we are going to be doing a little bit of material related to vectors in 6.4, but this is the last part of 6.3. Applications of vectors. So today we're going to learn about different ways that we can use vectors in real life. You know, vectors are used a lot in engineering. Vectors are used to represent certain natural quantities that have both magnitude and direction. And so we're going to see some examples of that today. Find the component form in SUV notation of a plane's velocity vector v if its speed is 500 miles per hour and its bearing is 240 degrees. Alright, a couple quick things before you get started. Remember that SUV just stands for standard unit vector. So you're going to give your final answer, your component form in SUV notation. That's the I's and J's. And then also notice that velocity is not the same as speed. Velocity is a vector with both magnitude and direction, whereas speed is simply the magnitude of a velocity vector. Also, last thing to remind you about, which we already learned, but when you're dealing with aeronautical bearings, such as this one, the angle is measured clockwise from north. Alright, so we're going to do this in two parts. You're first going to try to sketch, and then you're going to try and do it. So what I'd like you to do first, just to make sure you have the right sketch, is pause the video, do the sketch, and then resume when you have it. So this is the kind of sketch that you should have come up with. You have your angle of 240 degrees, which is clockwise from north, aeronautical bearing. You have your velocity vector, and it has a magnitude of 500. I can put in a reference angle of 30 degrees because, of course, that's just 270 minus 240, 30 degrees there. And I label the component vectors xi and yj. We're trying to find out what x is and what y is, but we know that whatever numbers we find for x and y, the corresponding vectors are just scalar multiples of I and j, since I is a horizontal unit vector and j is a vertical unit vector. Alright, so that's the sketch. Now, based on that, you should be able to figure out what x and y are using the trig that you know. So pause the video, figure out the component form, and then resume when you have your answer. Alright, so let's go through the solution. Now, I'm not sure if you thought of putting the negative, but that's alright, because this is the first time we're doing a problem like this. The reason for putting the negative for both y and x is you'll notice that the horizontal component is negative. That's because it's going to the left. It's going west. And the vertical component is also negative because it's going down. It's going south. And by definition, you know, when we're dealing with horizontal, negative is left and positive is right. And when we're dealing with vertical, negative is down and positive is up. All right, so that's why we have the negative signs here. Now, why do we have 500 sine 30 degrees? Well, if sine of 30 degrees is opposite over hypotenuse, and my opposite here is y, and my hypotenuse here is 500, then 500 times sine 30 degrees must be y. Likewise, we can do something similar for x. If cosine of 30 degrees is adjacent over hypotenuse, that is x over 500, then x must be 500 times cosine 30 degrees. And that's why we have these two expressions for x and y. And the final answer is vector v equals negative 433.01 I minus 250 j. Continuing with applications of vectors. A car weighs 2,320 pounds. How much force must its engine exert to pull the car up a 15-degree ramp? Alright, I'm not going to have you pause and sketch this because you may never have seen a problem like this and you'll see what I mean when you see the sketch. So we're not gonna do the pause. The sketch looks like this. Now, you've got your car there on the ramp. That part is easy, and you have a 15-degree ramp. You know that it slopes upward 15 degrees. But what's often difficult for students to understand the first time they do these, and you'll probably see these again in physics. The thing that's difficult for students to understand sometimes is that we're used to dealing with horizontal and vertical vectors. But notice that the combined vector, or the total weight, is my black vector that goes straight down. And so that's my vertical vector. However, we can still use a similar process where we break that vector up, so to speak, into its components. The only difference here is that rather than having a vertical and horizontal component, this vector of magnitude 2320, the vector in black, has a normal and a parallel component. Okay, now what do I mean by that? Notice that I have this red vector labeled f sub n, and I have this blue vector labeled f sub p. Well, f sub n is the abbreviation for normal force, and f sub p is the abbreviation for parallel force. Now, this normal force is not called normal to distinguish it from an abnormal force. That's not the sense. Normal in this case just means perpendicular. That's another way, very uncommon. Not in normal speech. We don't we don't we don't say we don't use the word normal for perpendicular. But in physics and in math, if you hear of a normal force, it means a force that's directly perpendicular to the object. Notice that this object, this car, is slanted upward. It's slanted at 15 degrees. But the red vector, the f sub n vector, is exactly perpendicular to the car. It's perpendicular to the car. Or, if you like, you can think of it as perpendicular to the slope. After all, the car and the slope have the same angle, so it's f sub n is perpendicular to both. Now, look at this blue component vector, f sub p. That stands for parallel force. And this is the component of the force that is parallel to the car and parallel to the ramp. And sure enough, if you look at this blue vector, you'll see that it is parallel to the ramp. It's parallel to the car. All right, so it's still the same trigonometric principle. The only difference is that we're breaking up a vertical hypotenuse into its normal and parallel components. Now, the other tricky thing about problems like this for students when they're doing it for the first time is figuring out this angle. Okay, now look, I'm circling with the mouse arrow this angle of 15 degrees. And what's not always clear at first sight is why that angle is the same exact angle as the ramp angle. Well, let's look at why it's true. Okay, if you look down here at the bottom at this dotted line, the dotted line is just a line that's parallel, a horizontal line that's parallel to the base of the slope. You can draw that dotted line anywhere. It's just to help you visualize. Now notice, if that dotted line is parallel to the base, well then this blue vector FP must be at the same angle, as the actual slanted portion of the ramp, because F sub P is parallel to the slanted portion of the ramp. And so it makes the same exact angle with the horizontal, and that's why this angle here that I'm circling now with the mouse arrow, that angle there is 15 degrees. Alright, now if this angle here is 15 degrees, then the angle adjacent to it must be 75 degrees. And the reason it must be 75 degrees is because 90 minus 15 is 75. And so if this angle that we just found here, the adjacent angle, if that's 75, and this of course here is a 90-degree angle because the perpendicular is always 90 degrees to the parallel. Well, then that leaves 15 degrees as the only possibility for this remaining angle here. Alright, so that's just a quick proof. You obviously don't need to sketch it this way every time you do such problems. You don't have to sketch it this way. But it does help for this first sketch to see why it's exactly the same angle as the ramp inclination. Alright, so based on this sketch then, you should be able to figure out the rest just using the trig you know. So pause the video and then resume when you have an answer. Alright, so going through the answer now, f sub p equals 2320 sine 15 degrees. How do we know that? Because the sine of 15 degrees, and I'm talking about this 15 degrees here that I'm circling with the mouse arrow, the sine of 15 degrees is opposite over hypotenuse, f sub p over 2320, and therefore f sub p equals 2320 times sine 15 degrees, and that's 600.46 pounds. And the last application of vectors is airplanes. A plane is flying with an airspeed of 500 miles an hour at a bearing of 330 degrees. It encounters a steady wind of 70 miles an hour in the direction of exactly northeast. What are the ground speed and true bearing of the plane? All right, so a few things to point out with this problem. Airspeed is just it's just the speed that a plane has if all you're taking into account is you know, how fast the engines are going, how fast the thing's going through the air. That's airspeed. All right, but ground speed is the speed of a plane when you also take into account any winds that may be interacting with the plane. You know, some winds hinder a plane, like headwinds. Some winds help a plane, tailwinds. And diagonal winds can have mixed effects on planes. So ground speed is the speed of a plane taking into account the effect of wind, whereas airspeed is the speed of a plane without taking into account the effect of wind. And also one other thing to clarify with this is when it says steady wind of 70 miles an hour in the direction of exactly northeast, that means that it's blowing to the northeast. It's blowing to the northeast. It's coming from the southwest, but it's blowing to the northeast. And that's what is meant by this 70 mile an hour wind. It's going to the northeast. And exactly northeast means as much north as east, which is a 45-degree angle. All right, so as a challenge, you should pause the video, try to draw this. Remember that vectors can be drawn anywhere, whatever's easiest for you to visualize. And so after you have the sketch, then resume the video to make sure you have the right sketch. All right, so here's the sketch. Let's look at the different elements of this sketch. Let's start with what's probably the easiest one, and that's this blue vector. This blue vector, I'm calling it v sub a, just to stand for airspeed, and its magnitude is 500. The direction we figure out because we know that the bearing is 330 degrees, and that since that's clockwise from north, then we're going to end up with a reference angle of 60 degrees in the second quadrant. That's why I have 60 degrees there. And then if we look at the wind vector, this red vector here, it has a magnitude of 70. V sub w, wind vector, has a magnitude of 70. And the angle it makes with the horizontal is 45 degrees because it's blowing exactly to the northeast. The black vector is what we would call the resultant of the two component vectors. But don't think of these components as belonging to the black vector as we were breaking up before vectors into their components. In this case, what we would think of with vector v sub a and vector v sub w is that they are acting together to produce a result. And the resultant vector is v sub g. Okay, so we can see that if we're looking at this in terms of vector addition, v sub a plus v sub w equals v sub g. Now, this v sub g vector, let's talk about this a little bit. This v sub g vector, of course, the g stands for ground speed. We can see what effect the wind has on it. It's blowing the plane a little bit. It's blowing the plane a little bit to the northeast, affecting its direction. And you can see also that it's not going to have such an adverse effect on the magnitude of the velocity. In fact, it might even help it, but we won't be able to figure that out for sure until we do the problem. All right, so what we're looking for then here in this problem is asking us for the ground speed, and so we're looking for the magnitude of v sub g. We're looking for the magnitude of v sub g, and we also want the true bearing. Now, this original bearing of 330 degrees for the blue vector, that you could think of as the intended bearing, or the initial bearing. But what happens is, because of the effect of wind, that bearing gets thrown off a bit. And so this theta prime here that I drew, this theta prime, that's an angle that you can consider your reference angle for the true bearing. Because just as 60 degrees is the reference angle for 330, because it's just 270 plus 60 is 330. Well, in like manner, 270 plus theta prime will give me my true bearing of this black vector, v sub g. All right, at this point then, I think what you can do, let me just explain the strategy. Explain the strategy, and you're going to follow this strategy. All right, so let's look at this blue vector with magnitude 500. Well, you know that you can always write a vector in component form, which means that you can break up this blue vector into its vertical component and its horizontal component. You can also do the same thing for the red vector, break it up into its horizontal component and its vertical component. And then when you have both component forms, you just add VA and VW and you get V sub G. All right, so let's see if you can figure out how to do that based on what I said, that strategy. If you can't, don't worry about it, because this may be new for you. So it's okay if you get stuck to unpause and then get some help. But at this point, pause, try to figure out the component forms of VW and VA, and then use those, add them to each other to find the component form of V sub G. Okay, let's look at the wind vector first. We have a horizontal component of 70 cosine 45 degrees. Of course, since cosine 45 degrees is adjacent over hypotenuse, and the hypotenuse is 70, well then, of course, the adjacent side, or the horizontal part, is going to be 70 times cosine 45 degrees. And similar logic governs our putting 70 sine 45 degrees before the j. All right, and then when we do that calculation, we get 49.4974747I plus 49.4974747J. You may want to have more decimal places than that, but I just kind of ran out of space on the screen. The main point, though, as you can see, is I'm not rounding off early. It's not a good idea to round off until you have your final answer. Now, breaking up V sub A, we have negative 500 cosine 60 degrees I plus 500 sine 60 degrees J. Now, you might be wondering why it's a negative 500 cosine 60 degrees I, but just to explain that a little bit better. Remember how in the last example we had to be careful about which quadrant we were in, because that determines whether horizontally we're going left or right, or vertically up or down. So if you look at the V sub A vector, Notice that horizontally it's going to the left. That's a negative horizontal component, but vertically it's going up, and therefore we have a positive vertical component. And so doing the calculation, V sub A in SUV notation is negative 250I plus 433.0127J. Now recall that the black vector, V sub G, is the sum of vector A and vector W. So V sub G equals V sub A plus V sub W. And since we've calculated V sub A and V sub W, we can find the vector sum simply by first adding the horizontal components and then adding the vertical components. And this is what we get. 49.4974747 minus 250 is negative 200.5. That's where the negative 200.5i comes from. And 49.4974747 plus 433.0127 is 482.5, and that's where the 482.5j comes from. So this is V sub g in SUV notation. And now we're ready to answer the original question. We want to find the ground speed, that is the magnitude of V sub g, and we want to find the true bearing, that is the bearing of V sub g. Alright, so magnitude of V sub g equals square root of negative 200.5 squared plus 482.5 squared, and we get 522.5. And theta prime, remember that to get the bearing we want to find theta prime first, since it's easy to work with acute reference angles. And so theta prime equals arctan 482.5 over 200.5. Notice again that I simply disregarded the negative sign for this because all we really care about is the theta prime, and it really doesn't matter what quadrant we're in for getting theta prime, since all it is a reference angle. And so it's easier to do without the negatives, and actually not only is it easier, it prevents ambiguity and confusion. So 42.5, that's our opposite. 200.5 is our adjacent, opposite over adjacent. The arctan of that is 67.4 degrees. Final step, the bearing equals 270 degrees plus 67.4 degrees, and that is 337.4 degrees, which is the angle clockwise from north, or in other words, the true bearing of vector V sub g. Final answer, writing it out in a sentence, the plane's ground speed is 522.5 miles per hour, and its true bearing is 337.4 degrees. Here's the classwork, page 458. Please write these numbers down, and see you in class.